Aspiration. Hey, why is that funny? Yeah, thanks very much. Thanks so much. It's always wonderful to be back at MSRI. Thank you to the organizers for this awesome conference. And yeah, if you have more questions about my name, I'm happy to take questions afterwards. Okay, so what I want to talk about today is a very old question in analytic number theory about understanding square-free values taken by a polynomial. So I won't go too much into the history of what is known about square-free values of polynomials. This being an analytic number theory conference, the general problem of understanding how often multivariable integer polynomial takes square-free values is in general unknown. In fact, if you take the polynomial x to the 4 plus 2, it's not even known that it takes infinitely many square-free values. For one-variable polynomials, one does know the density of square-free values, assuming the ABC conjecture. But for general multivariable integer polynomials, even under ABC, we don't know how often multivariable integer polynomials take square-free values. So that's a general unsolved problem. But if you have a certain polynomial in mind that you need to know the square-free values of, then you can hope to maybe exploit the special shape of the polynomial that you have, use any extra known structure of that polynomial to try and determine the density of square-free values by exploiting that extra structure. And so that's what I want to talk about today for a particular polynomial that comes up very often throughout mathematics, in particular number theory. So this work that I'm talking about is joint, I should have said, with Arul Shankar and Jerry Wang. And the polynomial that we're interested in is the discriminant polynomial of a polynomial. So if one takes a monic polynomial of degree n, and you take its coefficients to be indeterminate, and you take its discriminant, then the discriminant is itself a polynomial in the coefficients of your polynomial with indeterminate coefficients. So just to be concrete, so if you take the discriminant of the polynomial x squared plus a1x plus a2, okay, so we'll always take monic polynomials with indeterminate coefficients a1 through an. We're talking about degree n polynomials. This is degree 2. The coefficients are a1 and a2. And the discriminant, as we all know, is a1 squared minus 4a2. Okay, and if we have a degree 3 polynomial, we can take its discriminant. It has coefficients a1, a2, and a3, and its discriminant turns out to be that expression. And then I didn't write down the quartic one because it would have taken the whole slide. But in general, delta n, the discriminant of a degree n monic polynomial, is a polynomial in n variables, and its degree, its weighted degree, is n times n minus 1. If you view the ith coefficient ai as having weight I. Okay, so for example, you can see in the degree 3 case, right, each of these terms here has degree 6. Okay, if you view ai as having degree I. So you have a3 squared, you have a2 cubed, okay, all degree 6. So the discriminant is defined as the